I think it's time to start the second part of the session. We'll have a talk by Stefan on porting MedGraph to GPUs. Stefan, you have 30 minutes, including the discussion. And could you please start sharing?
Yes, just a moment. Okay, and then let me go full screen. Can see the slides?
Yes.
Okay, thanks. Okay, so hello everybody. I'd like to talk to you in the next couple of minutes about the work we have started this year in porting MATGRAPH to GPUs. So first slide, a bit of motivation and also a bit introduction. So as Josh also said already before, there is especially for the high Lumi LHC area, there's a lot of CPU demands, especially for simulation and Monte Carlo event generation, and the MATGRAPH event generator is especially used by CMS and also Atlas. So the aim is certainly to produce something useful for this era and for the experiments. Then, in the context of the work that we have been doing, it's important to stress that MATGRAPH is a code generator. So basically, what you do is you give to MATGRAPH the physics processes that you want to simulate. And then MATGRAPH itself is written in Python, and then it has several backends, and it produces source code, and you're compiling the source code, and then the resulting binary is then the one that you are using in order to do your event generation. And the backends that MATGRAPH has are in Fortran, C, C++, and my understanding is production version on the grid is mostly Fortran, but we have been concentrating on C++. And then also MATGRAPH is integrating a lot of other functionality like random number generation, pattern distribution, phase-space sampling, and so on and so on. So before going more into the engineering part, let me talk a bit about the people. So we are very lucky that we have established an excellent collaboration with Olivier Matelar from Université Catholique de Louvain, who is one of the core MATGRAPH developers, and he's basically he's giving us a lot of insights, and also he's porting all our developments upstream. And then there are several people who are contributing part of their time to the various parts of the development project. So for CUDA development, this is Andrea, Olivier, Stefan is a new LD that has joined us, and Taran from Andrea, Stefan are from CERN. Taran is a student from Bangalore, and myself, and then many other people are working on abstraction layers, namely David Lawrence, also from CERN, and then Smita, Taylor, Tyler, Walter, they are coming from Argonne. So as MATGRAPH is a code generator, the software engineering process looks a bit different for us, which is that basically what we have done is we have started, as I said already, with the C++ version. So we let MATGRAPH produce us C++ code, and then we took this code as a baseline, and we have started porting this onto GPUs. And once we had done this first iteration of porting, basically we are now entering a loop where we are developing the code. Olivier takes our developments, ports them upstream into MATGRAPH. MATGRAPH regenerates, auto-generates the code that we have just been developing. And then we start a new development epoch, as we call it, on top of this new generated code. And in each of these epochs, we are optimizing, we are putting new features and working on more complex physics processes. And we are using these also as baseline for the abstraction layers. So looking further a bit into the Monte Carlo event generation workflow, this is what you see on the right is a picture from Andrea, where he describes the workflow. So basically, you start with random numbers as input. You calculate Feynman diagrams, which I'll come to later, is this matrix element calculations. And then you have a feedback loop once where you can optimize your workflow. And then once you have optimized, you basically go into mass production. Now, for the purpose of this engineering work, I've simplified. I mean, this is basically the same picture, but I'm reusing it throughout the talk, so I've simplified it a bit. And I would like to use this slide to talk a bit about the specifics that we have with the engineering that we are doing. So one thing I mentioned already before is that we are starting from random numbers. So this is very different to all the other workflows because Monte Carlo event generation is the first one in the simulation chain. And we given that we can produce the random numbers on the GPU, on the device, we have no input data. So and usually it is a lot of hassle always to copy data over to the device or from the device back to the host. So this is one specific thing. And then for the parallelization, we have chosen that we are basically parallelizing on the event level. So if you take a CUDA core and one core is going through the whole chain of the random number generation, the phase space sampling, matrix element calculation, and so on and so on. And then if you have 2,500 of those cores, you run basically 2,500 events at the same time. The nice thing about this is basically that the only thing that differs between all these cores that you are executing is just the random number that you're feeding into the process. So every of these threads is basically going through exactly the same execution path, and this is also something that maybe hits a lot of other software projects, which is thread divergence. So for us, we are starting at the same time and we are stopping exactly at the same time. So this makes it also very, very convenient for doing this. Okay, so now where to start? So this is actually, I think it was Effe who gave me this. This is an example from CMS. So we started with profiling this process that you see on the top. And this is the Fortran version. And this is a flame graph at the bottom. And you can basically, you can do a grep on all the parts of the workflow that are doing, for example, matrix element calculation, and you come out with 78% of the CPU time, which are spent in matrix element calculation. So this was naturally the place where we started the porting. Now, for the porting, we have not taken this very complicated process, but we have taken actually the simplest one that we could imagine. And this is E plus E minus to mu plus mu minus. So you see these are just two Feynman diagrams. And the C++ code that MATGRAPH generates for us is 500 lines. And at the bottom right, you can see the dependencies between the different functions which are used inside MATGRAPH in order to calculate this Feynman diagram. So this is something which is very nicely overseeable, I would say. Now, so we are entering now this initial epoch. So this is really the C++ code that we had taken from MATGRAPH. And during this initial epoch, basically we made the CUDA we made the CUDA version run basically on the GPU. So we had to deal with we had to reorganize the data structures. We had to call the kernels correctly inside the kernel, distribute the work. And at the end of this epoch, of this first epoch, we ended up with something like a factor 200 over a single-threaded CPU process. And then we, as I said already, we gave all these developments. I mean, Olivier also contributed to this, but then in addition, he took all the developments and ported them upstream into MATLAB proper. So in summer, basically we started the first EPOCH 1, so on top of this. And the first thing we did was that we regenerated the E plus E minus code. Now, as MATLAB could do this, we could also generate more complex codes, for example, gluon to TT bar gluon, or even more complex codes like the gluon to TT bar gluon. And you can see that the complexity goes up quite a lot here with the dependencies that are being called within the kernel itself. So for the software engineering during this epoch, we have ported more parts of the workflow onto GPU, namely the random numbers. It's a very simple phase-space sampling, which is called Rambo. And then we have done a lot of work with the data structures. Namely, we had removed all the STL. And then this was Andrea who contributed a lot, or he did most of the work in this area. We introduced a lot of switches. For example, we could run the whole workflow in double precision or in single precision. We worked on the data structures, so we can switch between arrays of structs of arrays, arrays of structs of arrays. And then we had different implementations for the complex arithmetics, which is very important for these computations. And again, we made the same code again run in pure C++, so we can easily compare host only and CUDA version. And then we did a lot of work also on profiling. Now, looking into the profiling, this is a profiling plot of the overall workflow at the top that you can see, and at the right you can see these 10 iterations that. So we're calling the kernel 10 times with these numbers of blocks and numbers of threads, and then the more interesting part is then if you look at the bigger picture. This is one of these iterations, and you can easily distinguish here the different parts of the workflow. Number generation, the phase-space sampling. Then we are copying back all the weights and the form momenta back to the host. And then here the little blue part there in the next to it is actually the matrix element calculation, which is, you see it's tiny compared to the time we're using for data copying. And then at the end, we're copying also the matrix element values. So as the physics process was very simple, I think the conclusion that we had is that this is much too simple, and we have to go to more complex processes. Now, still with this E plus E minus to mu plus mu minus example, if you look at the performance, so basically, when you take only the matrix element calculations and the copying back of the matrix element values to the host, we are approaching a factor 1,500 over a single threaded CPU. If you take also the phase-space sampling and the other two copies that you have seen before in the previous slide, then we are around a factor 200. Now, we do imagine that both these numbers will improve once we get into more complex processes for the physics. Sorry, wrong direction. Now, just to flash quickly, another thing that we are doing is we are aiming now to run our workflows as many platforms as possible. So basically, you can imagine this as a two-dimensional grid of CPU flavors versus GPU flavors. This is, of course, we want to run on the HPC centers, and there are many different flavors coming up. And we are also working very closely with the WSEG benchmarking team, which would like to also be able to test, and we would like to also test our performance, of course, on these different variations. Now you can imagine there's also a third dimension to this. I mentioned already all these abstraction layers that we are investigating. So basically, you can imagine that we would like to also test this versus CUDA, HIP abstraction layers like Alpaca, Cocos, One API, and so on. And there, I just wanted to flash one slide from Charles here, who showed during the CC kickoff workshop in March some metrics which are not only performance but many other metrics that you can imagine in order to evaluate these different implementation languages and abstraction layers. Okay, so the status of this is, as I said, we're working towards Alpaca, Cocos, SQL, One API. We have first implementations already in the repository for this E+, E-, mu plus, mu minus, and the remaining ones are in the works. So just to say, Epoch 2. So we are now we're again in the phase where we're porting our developments upstream. So this is something which is currently happening, and we will soon start to develop on top of a new generation of auto-generated code. So this is about future work that we are envisaging. So this is things that we were looking into, for example, CUDA streams. So in order to hide the latency of the data copy, we're also looking into CUDA graphs. There were very promising results, but we have to cross-check these numbers. And then just to say, for the software engineering part, we are fighting a lot with register pressure. So every streaming multiprocessor on the GPU has a defined number of registers, and we're eating them up very easily because a lot of the calculations are done in complex double precision, and then each number basically is using up 4 registers. So we have to think about how to get this register pressure down. I mentioned already single precision versus double precision. Now we can run our workflow in single precision. We are estimating a factor 2.4. But this is also, of course, a physics question of if this is affordable. And then one thing we haven't looked into is yet to engage the host into the calculations. So there are still CPU cores that we can use, and for the CPU version, we'll have to look also in vectorization of the data structures that we have engaged with, and the hardware abstractions. Okay, so this is maybe more for the computing coordinators. So this is what we would be still missing in order to, what I imagine what we would still be missing for having a useful workflow available for example, for LHC experiments to calculate. So I mentioned already the phase-based sampling and phase-based optimization. So at the moment we're using this Rambo, which is a very simple phase-based sampler. So we should be optimizing and replacing this with something more complex. And there is just next talk will be on Vegas flow. So this could be very interesting to look into. Pattern distribution function, we haven't started yet at all. Again, PDF flow in the next talk. I'm very much looking forward to this. And then for the Monte Carlo integration and Monte Carlo unweighting, we are currently actually doing this as we speak. So more things that we have learned in July, and this is what I really recommend. We have attended a hackathon, which is coming from this GPU hackathons.org series. This was extremely useful, and we had a lot of positive input from our mentors, and this was really a boost to our project. And then what we also observed is that many other teams in many other areas are currently starting to program for GPUs, and basically there's a fundamental software engineering level which spans all the different fields. So there is a new forum which we call Compute Accelerator Forum. We would like to discuss these fundamental aspects of software engineering for accelerators. And then for MATCRAF itself, we are, as more people are joining, we have to get better organized and we have moved to a proper GitHub organization, better structure in the repository. So in grosso modo, a better organization. So in summary, so I would say from a bunch of goals who were attacking the code in spring, we are getting more and more organized now. And the second slide here is so to say that we have started the porting of MATGraph event generation on CUDA. We have 3 parts of the workflow, namely the random number generation, the simple phase space sampling, and the matrix element calculations are ported. The speed up factors range from a factor 200 to 1500. This is mostly due to the simplicity of the underlying physics process that we are using, and we have to port more parts in order to be usable for the LHC experiments. And what is very important, that all our developments are going upstream, so they are really MATGraph now has in addition to Fortran C++ has a CUDA backend, and can generate already this CUDA code that I've shown you. So there are a lot of people I would like to thank. I'm running out of time. So, but still there are many other people who are contributing to the infrastructure, to testing platforms and so on. So many thanks to all of those. And the last slide, I just want to give you some pointers if you're interested in this work. And that's all I had. Thank you.
Thanks a lot for talking about these nice developments. So any questions or comments? I see Enrico raised the hand. Please go ahead. Enrico, we don't hear you if you are talking.
Can you hear me now?
Yes.
Yes.
Oh, excellent. Sorry. Yes, thank you for the talk. So I was wondering about how this new effort is related to earlier efforts to port MATGraph amplitudes to GPU, because there were some efforts, if I remember, starting even in 2010 or something. So I was wondering if this is a completely new effort, or if there are things that you are doing differently, or
yeah, I guess you're referring to the KK efforts, the GVegas and GBasis.
Yes, I believe it's a Japanese group, right?
Yes, but this code has been taken on by the Argonne people, and they have, first of all, what they have done is that they have ported this now to the latest CUDA version. And this is one possibility how we could have a better phase-space sampling and phase-space integration. But, or are you referring to other efforts which I may not be aware of?
No, that was the one. I was just wondering like, if you are building on top of that, or if you're doing something completely different.
No. I mean, we have been, I mean, so far the CUDA developments that we have been doing is basically, well, the Rambo phase-space sampling that we have been using is very simple and extremely inefficient, I understand. But it's a way in order to get the workflow going, and we have to come with something better. And this initial work of the Japanese people is taken on by the Argonne people and taken on board by them.
Stefan, if I can add one thing, it's Andrea. My understanding is that actually the KEK team had worked both on Vegas and Basis, which, as Stefan said, the Argonne team are now looking at. But I think they had also done some work on the matrix elements, which, however, I think that this was using an earlier version of MATGraph. Now, Unfortunately, Olivier is not here. I think it was using HELAS, while now essentially the engine is called Aloha, which is slightly different. So that's one difference. And the other difference is also that I think they were using a very old version of CUDA. So yeah, we have not really looked at that. We kind of restarted from scratch.
The Vegas part has been ported.
Yeah, the Vegas part, yes.
It's now at CUDA 11. Yeah.
Yeah, there is no big difference between Aloha and HELAS, actually. So indeed, they were using HELAS, but they were also actually at some point using Aloha for that. So that's not a huge difference. But indeed, they were using mainly CUDA 4. And our work, I mean, we read their paper and we basically reproduced some of the tricks they were using. So we are not really restarting from scratch on that point of view. We're building on what they are doing. They identify some stuff that are useful and we have implemented that as well, actually.
Thank you.
Raise the hand, please go ahead.
I didn't quite hear who you were asking, FA, but I see Stefano at the top.
Stefano is raising a hand.
Yeah, the question that I have is, yeah, of course, this is extremely impressive, but you know, the factors that you quote, the 1,500 and 200, are a bit misleading because everything is flat, right? And one of the crucial things for the integration of the cross sections is that the integrator learns as it goes. Mm. So my question on, you know, when porting Vegas, Basis, whatever, onto these new techniques is whether these crucial characteristics will be maintained rather than, you know, simply parallelized without any crosstalk with the previous interaction, because that will be crucial, especially for beyond leading order computations.
Yeah. I mean, I can give you a software engineering response, which is, I mean, if you look at, I'm still sharing, yes, yeah. If you look at this slide here, I mean, we are basically what we are copying back here is all the weights and all the form momenta that are generated. Now, of course, in practice you don't need this to do this. If you know better about your physics process, but maybe also Andrea, Olivier, you want to add something?
Well, maybe I can add. I mean, what we are really speeding up at the end of the day is the time of the computations of the matrix element, and that's completely independent of basically your phase space integrator. So indeed, when we have a phase space integrator implemented, we'll reduce the amount of data we need to transfer back from CPU to GPU, and that's will improve stuff. But also, I mean, it's I guess completely orthogonal to the phase space integrator on that point of view. What would be annoying for NLO is, of course, the fact that we are not able yet to compute loop on GPU, and that will be, of course, I mean, quite a lot of work to do that. And that will be the main issue, to my point of view, to move that, I mean, to go to NLO computations.
So, Olivier, I'm not sure I understood you. So you're saying that adaptive integration will never work on GPUs?
No, I mean, I just said that it's orthogonal to what we have done.
Of course, yeah, this I understand. But my question was whether the other part, namely the adaptive integration, will ever work.
I mean, there is already two versions done by Kaoru Agiwara, right? One GVegas, one GBasis. We were doing that on GPU. So yes, it should work.
Okay, thanks.
Okay, Charles, raised hands.
So as you start getting into some of the more complicated processes, do you see any indication that this might become more compute bound or memory bound on the GPU?
Yes, I mean well, compute bound for sure. I For sure. We have after this first version of MATLAB where it can auto generate the code. We have now CUDA versions of these processes that I showed you, the gluon to TT bar gluon and so on. We have not done the performance comparison of this. This would have been a good thing to do. So I would expect that the sigma kin kernel here, which is the matrix element calculation, grows dramatically. But yeah, I have no proof.
I can comment a bit, Stefan. So the last time I checked, so for E plus and minus to mu plus minus, there we are completely compute bound. While for the GG to TT bar 2G, the latest time I checked, which is not the latest version, we were actually memory bound. The issue is that we are using mainly too many registers, and therefore there's a lot of transfer to global memory, and that was our limitations. Now we have still made improvements, and I didn't rerun the compiler on it and the profiler on it, so I don't get the latest result. But I expect that for big computation, we'll still be at some point on the memory bound due to that, actually.
Yeah, I mean we are already experiencing with E mu mu some problems. For example, we're overflowing the registers, for example.
Do you think there's any possibility of using some of the B-float data types?
Sorry, say again?
Do you think there's any possibility of using some of the B-float data types, or even reduced precision?
Yeah, I mean we can run our complete workflow with one switch. We can move from double precision to single precision. We can execute it. Now, if it's useful, this I would say is something that the physicists have to discuss, and maybe it will also only make sense to move parts of the workflow to single precision. So, but this is not something which we from the software engineering side I think we should decide on.
Cool, thank you.
Okay, so we ran out of time for this talk, so we could follow up all the remaining questions from the Google Doc.